My name is Phil Meis, and today I'm president of Utility Mapping Services, but I'm here on behalf of the American Society of Civil Engineers to discuss and present to you an overview of two standards that are being rolled out as we speak. ASCE 3822, many of you are familiar with the ASCE 3802, which is a 20-year-old version of the standard for investigating existing utilities. And so we're going to talk about the 22 version, just kind of touch on the changes, the differences, and again, we're going to have to stay at a 30,000 foot level at this for this time frame. And then I'll also be talking about ASCE 75, which is a standard, a digital standard, data standard for documenting utilities and exchanging the data, and really enabling a lot of these really neat tools, technologies that I'm seeing coming up on the during this presentation. It's kind of fun to see this stuff because these are the standards that'll really make those technologies fly. So the key takeaways, we're gonna, because of this audience, obviously we can glance over the first and the last bullets, and we'll focus on the middle three. Everybody knows that utilities are at risk, and that's why we're all here. And the technologies, as I mentioned, that you guys are presenting are emerging, and it's really fun to see that happening. But we need the good, accurate data behind to make those technologies fly. And as we all know, we kind of let ourselves sleep at the wheel here. The issue kind of sneaked up on us where we only had one gas company, one Ma Bell, and it wasn't really much of a problem. Now we've got so many things out there. It's really changed to where we have to up our game on how we manage data. And the best time to do that is, what I'll talk about, the ASCE 75 is documenting them at the time of installation. I mean, that's really kind of a no-brainer. But so we know utilities are at risk. This is it's really become a major issue, especially in urban environments. This is actually the same street, and going out after the fact and trying to paint the ground and recreate what's out there is really a horrific operation, and obviously some cases almost impossible to do. And what we're doing is we're winding up with a lot of issues, paint on the ground, trying to work that into the plants. That's really kind of a primitive way of doing things here, but it is a damage prevention process. It's very important, but it's not very conducive for design. And these standards that I'm talking about from ASCE are in mind, backing it up to when we're in the design stages and trying to get things right so that we can get our designs right to mitigate issues with the existing utilities and try to expedite the construction. We're spending way too much time in the field trying to adjust things, pushing the risk to the contractor. And obviously we know that these are troublesome avenues to take. So as I think Paige mentioned earlier, that the Common Ground Alliance did an investigation. Just I think the last report, or 2019, they documented about 500,000 strikes in the U.S. And if you figure that over a 10-hour workday, that's a strike of about every minute. So I saw that earlier where I think in Ontario, there's this gas line getting 7 of them are getting hit a day, I think. Anyway, that's so, and it's only going to get worse as we open up our right of way for 5G installations to connect up communities and replace old infrastructure. We have a population growth, so we have to expand it. We have renewable energy sources that we have to collect, and we have charging stations we need to install. So it's really getting exasperated in the U.S. and I'm sure in Canada. If you're going to be putting in charging stations, you're going to need to install high voltage DC transmission lines, which is one of the things that enables high speed charging, and they require some space. So again, it's just getting worse. So that's why ASCE stepped in. American Society of Civil Engineers said, look, what the engineer does and puts out there for construction has a multitude of impacts to the traveling public, the safety, the project schedule, contractor risk, and the ratepayers and the taxpayers all pay for it. So it really goes back to public welfare, and that's why these standards are engineering standards. What we'd like to do is enter into a world where we can have things well laid out, well understood, in the design stages, and then start applying 3D design technologies, virtual design and construction technologies, and make it so that the construction experience can go as fast as possible with the least amount of risk and issue. And that's going to save everyone money and a lot of headaches. And indeed, we have some examples. We can go back. This is 7 years ago now, but this is a project we were involved with, where we were able to collect data in 3D by using some extra methods and technologies, ground penetrating radar and using some of the electromagnetic tools. But we didn't have a way to really depict that information. And this was the first use of Bentley's SUDA application, where we were the beta testing team for that application. So we were excited to apply it for an actual project, a gas main installation. And we mapped all the utilities out in 3D. We designed the gas main in 3D, and the value that came out of that was really surprising. I mean, we kind of suspected that, but by having things where you can view it, the DOTs, the DOT officials that were reviewing the permit application were able to actually see why the gas main wanted to go where it did out in the road, where they wanted an open cut and they wanted a depth variance. And initially, the DOT, they told us afterwards, they went into the meeting with the mindset, we're not going to let them go under our road. But then after they saw the congestion and why the alignment was selected as it was, it's a high pressure gas main, you need to get that out of harm's way. They actually granted an open cut and a depth variance waiver, because and the contractors at the pre-bid came in, and instead of all these plans and cross sections and profiles that they're so used to dealing with, they looked at this, and we had the model up, and we showed them exactly where all the crossings were, where all the unknowns were identified, and they knew where they're going to have their bends and where they're going to, all their quantities were laid out for them. So they said this is the best bid package they've ever seen. And the engineers estimate that came in, this is an actual project for out in the West Coast in Washington, came in under 10% under the engineer's estimate. So already, at this point, you've already paid for going out and figuring this out many times over. Now, the work that was scheduled was for 10 weeks and 2 crews, because they had to go out on a busy road and work at night. And so they only had a limited time span to get that gas main before the school season started again. So they scheduled 10 weeks and 2 crews. Everything was exactly the way it was told. They built the whole thing in 7 weeks with 1 crew. Okay, so that should tell you right there. I mean, you don't have to be a brain surgeon to figure this out. You get your ducks in a row going into the project. You can build a project and get it out of there a lot faster. No damages, no delays, no changes, which is really unprecedented in this for gas main installations. I mean, it was for this nature in an urban environment. Typically, you're doing field fits and you had delays. Public and commerce were not affected. In fact, they had DOT people traveling that road. They didn't even notice the work that was being done. So it was one of the very successful projects. It was built as designed. So that's just a case study, just to show how valuable, how much value can be reaped by having your data good going into the design and into the construction. So there's 2 standards, 3822. That's in both, and both of these standards, by the way, are on parallel tracks. They've both gone through their public comment. They're in for at ASCE pubs right now, and I suspect that they will be out for publication. I mean, for consumption within the next month or 2. If Jim Ansbach's on it, he's probably going, it's going to be 2 months. But anyway, it's right there. And I'm going to talk about 38 first, and I'll talk about 75. 75 was, it's basically a sister standard for 38. And I would suspect at some point in the future, these 2 standards will merge into the same standard. 38 addresses the fact that we didn't keep track of that stuff when it went in the ground, and we're trying to figure it out after the fact. So it basically addresses the symptoms, but it doesn't resolve the problem. And 75 says, let's track it when it goes in the ground in the first place, or if it's exposed during construction, let's get it right and get this information. And it's not saying what technologies to use. We're just basically saying this is the data you want to collect and manage. And there's another standard I'll mention at the end, OGC, Open Geospatial Consortium, which is a standard for making that data from 75 interoperable, so that you can basically seamlessly transfer it to different softwares and applications. 38, we'll focus on it real quick. It's an industry standard. I know there's a number of Canadian agencies that have adopted it, but I couldn't find the right kind of logos to stick them in here. You have to have transparent logos to make this look nice. Anyway, there are, I know the Transportation Association of Canada, Ontario, Edmonton, many cities, BC Ferries, they've all adopted ASCE 38 along with a lot of USGS or US agencies, and the Common Ground Alliance, both. Colorado, it's interesting. This has basically been accepted as a best practice in the US and in Canada. And Colorado went a step further and made it a law, requiring it on all their public projects, nearly all their public projects. And I can actually show you a case study here where we can compare some before and afters with it. But so it's I think this 20 should be 22 right now. This takes a little longer to get these standards up. It's an engineering product. I think it's important to understand that. Typically, historically, if you're just calling one call and doing a pickup survey or taking records and transcribing the plans, you're working with C&D data. That's what ASCE 38 would call it. And the idea with the 38 is to get it to B. What B is you've done a professional investigation, you pulled the information together, it's been analyzed. There's a professional that's actually going to put their seal on that submittal, and their errors and omissions going to back it up. And 38 has evolved to be a performance and a prescriptive standard. So there's teeth behind it as far as from a legal perspective. And then A would be exposed and discrete. So this is and again, the P is putting the seal to it, and it elevates it to a professional effort akin to a property boundary survey or a geotechnical investigation, however you want. This is an example here where again, this is just prior to the Colorado law change, where a project was going to go out to bid. The law changed and we had to go back on this project. You can see the data, the utilities that are depicted, it looks pretty good, but this is based on records and the conventional methods of pulling the information together. This is the same intersection. I'm going to just go back and forth here. This is after a 38 investigation and you can see the density of utilities is increasing, the alignments are changing somewhat dramatically. And anyway, these are just some of the things that were identified. I mean, there's quite a few things that were wrong. It's been documented as a very good process. ASCE 38, again, it's a prescriptive and a performance standard. You need to have pre-qualified people to do this work and be able to stand behind it. And your errors and omissions insurance that backs up that company needs to understand what that company is doing and sealing and be able to stand behind it. You need to understand the uncertainty so that the engineer can make, where information is more is required to complete the designs, so where they can modify and adapt designs to avoid conflicts. I mean, there's big decisions that are made with this data. You want to make sure that the information is right, and you understand where where it's right and where it's good and where it's not, and have that clearly identified. For the 38 investigation, you might know on either side of the street very well where that facility is, but where it dived under the street, say they bored it in and they went deeper than the geophysical methods can detect, then you have to fall back and to a lower quality level, or maybe use some of these nice new gyroscopic tools that we can, if you had an empty conduit. We want to accelerate the project delivery process. Again, time is money, and make the public experience, less disruptive, less painful. Make sure the project is constructible before the contractor even breaks pavement or breaks ground, and come up with solutions to problems before they happen. It's just measure twice, cut once mentality here. And we can get better estimates for the costs. We can communicate the risks, the stakeholders, and we can allocate the risks between the parties. And the idea is to avoid, accommodate, and then relocate. Now that's something that that's another thing. We have to change the mindset of a lot of agencies that manage the right of way, where they kind of let the utilities in there and say, hey, it's not our problem, it's the utilities' problem, they got to get out of the way. Well, that approach, as I mentioned, doesn't work anymore. And everybody's accountable and things go wrong, especially when a gas main gets broken and a building may get exploded. So if we can avoid and accommodate infrastructure in place, and you can take that out of the critical path for the project, you really expedite. That's the other thing. You can really save a lot of money by speeding up these jobs. What are the same things for 38? Well, a lot of the definitions, the 4 quality levels, the deliverables and standard attributes, the tasks, the values, and the methods that are used. But what's different? Well, there's specific performance goals now, and it's there's a lot of commentary added to help. When 38 came out, 3802, people, we didn't anticipate that they would actually read the standard, and then they kind of had their own interpretation. So we had to kind of help set them straight. Now, the intent of 38 is to get to level B and to level A. It's not to say everything's level D and then call it, hey, I met the 38 standard. And then we wanted to provide better definitions so that there's clarity. I mean, it was pretty obvious where things went wrong. We wanted to include aerial installations along with it. Now, there aren't quality levels assigned to the aerials, but they're basically, you want to map that infrastructure, include that with the submittals. It makes a lot more sense. And then there's an engineering report that goes with the submittals to help lay out, hey, this is what we found. This is what this is where we had issues. These are the discrepancies. These are things you need to be careful about. This is what the recommendations going forward in the project, what you need to consider, and where we may need to do better, more advanced geophysical investigations or vacuum excavations to better define it for completing the design and the utility coordination and preparing the construction documents and the construction planning. So it's a performance goal. As I mentioned, you have to, what I would say, the liability behind this is significant. Whoever's providing this service and providing this data needs to be able to document that they did sufficient work to stand up in a court of law and said, we met the standard of care. And this is our QMP. This is what we did to show that and protect the owner, the contractor, the engineer that the service is being provided for. It's a big deal. So the idea is, and why is it a professional work? Well, and I borrowed this slide from T2. Thank you, T2. But the idea is you're bringing a lot of different disparate data and information together, and you're looking at what's out there and what the data is showing, and you have to make an assessment and assign risk and reliability to the depictions and the models and the data, and then say, okay, I think this is where your data is. This is what it looks like this, and here's where, and make it clear to the engineers and to everybody, all the stakeholders, what that data set represents, so that they can make good decisions. So it's there's a lot riding on it, as I mentioned, a lot of decisions. So now I'm going to jump to 75. Again, we're staying at a high level. I've only got getting down there in my time here, but I'm not going to be able to touch on many things, but I will touch on a few key things, okay, of the standard. This is the appendix, or the table of contents. If we just focus on the content, now what we want to do is define the spatial and the attribution of the facilities, and just define what do we want to record, so that when we, at the end of the day, we can turn around and actually create a digital twin in a user-friendly format, in a consistent format that can be used for all these great technologies that we talked about that are coming out. So we wanted to, some key aspects is we want to have reference everything to absolute spatial positioning, have an accuracy with that observation, and then have a framework for the data exchange. By having a standard datum, this is a big deal. So I came from NOAA, the National Oceanic Atmospheric Administration. This is the same thing we do for nautical charts, hazards to navigation. We're just applying it to hazards to excavation. Everything is referenced to the National Spatial Referencing System. Why do you do that? Well, that gets rid of all the distortion that happens when you're trying to take something on a sphere and flatten it up on a flat plane. You get distortions. There's different projections, state plane, county coordinates, UTM, and they all distort the image. And by having everything referenced to the National Spatial Referencing System, when you bring it together, it's going to go in the same spot every time. And and it counts even for plate tectonics and coast, crustal drift, and places like California, that's a big deal over 20 years. So that's the one thing that and that's easy to do. Whenever you're turned on your GNSS system, you're tied into your National Spatial Referencing. Canada has a very similar, in fact, I think they're using the same one for North America. It's the National Spatial Referencing System is being upgraded, and it should come out, I think, in another year. The other thing is observations. I mean, now if you're using that LiDAR system we saw earlier, you can just pull data at this frequency or tighter frequency. The idea is to get enough observations to achieve the accuracy that's required with it. So there's an accuracy table that goes with the standard, which we basically piggybacked off of CSA 250, the Canadian standard. And we have CSA 250 people on our standard committee, by the way, very helpful. And the three things they told us was we want to see this succeed. There are three things we wish we would have done with CSA 250. One was make it digital, two was make it 3D, and three was to also include above ground infrastructure with the standard. So we made sure we brought that into 75, and I know going forth we're sharing our information back and forth, and you'll see that the standards are probably going to merge together and be very similar in nature. Another thing was the observations. So if you're getting the top center of the pipe, you record that, but what's exchanged will be the reduction, so it'll be the center of that infrastructure. So the center of the pipe typically. So items, there's data stewardship. We addressed things like if it's sensitive and secure information, that what to do. And there's standards that we are referencing here in the US. We're using 49 CFR 1520, which talks about how to manage sensitive and secure information. That's a big issue with a lot of utility owners. They don't want that information available to everyone. And basically that guidance is provided in the standard to make sure that information is kept secure. That alleviates their concerns. This is don't expect to read this, but you have a minimum and optional and conditional attributes. But basically we have one table for documenting infrastructure, and these are the minimum requirements, the M's. Basically we want enough information that we can create a digital twin or a very useful 3D model of that infrastructure in a standardized manner. We'll have to have maybe at the next conference, we can have a workshop and actually go through this. But this is just showing how it's applied in the field. You would take this, if say you're putting in the sanitary sewer main, you would take observations at a frequency necessary to achieve the accuracy standard. There's an accuracy table that goes with this standard, and then you're also going to take observations of anything exposed that you might encounter along the way, and document that as well. That's free data, and so not only document what you're putting in, but anything you expose along the way. So this standard can be applied for contractors for utilities when they permit to go on the right of way. It's a fairly easy to implement standard. Directional drilling, you'd have observations at the bore pits, and if you had a test pit where you had to bore through it, you could get accuracy levels to the accuracy that's required. And then in between, we also lean on ASCE 38, so you'd have ASCE 38 quality level B data where you would use gyro or other geophysical electromagnetic tools to get depth information, and that's all included. So every observation, where that data came from, if it was a direct observation or if it's quality level, and you have a horizontal and vertical accuracies that go with that. It's been the standard, just to put we implemented in the US and Montana under an MOU while it was still under draft, and it's been used for several years now in Montana with new installations at the time of permit. And we can collect all the attributes in an approximate alignment at the time of permit. Very easy to do. The person filling out the permit understands all those attributes and can plug them right in. And then when the actual work happens, basically the approximate alignment's upgraded to the actual observation, the survey data. This has actually received a national award as well as in Montana. So it's again, these tools can come into play now. The last comment I want to make is Open Geospatial Consortium has adopted both ASCE 38 and 75 as important input to their model for underground data definition initiative. And that the MUDDI model basically is your interoperable. I mean, that's your, if you bring the data forward, Bentley, has they're you can view it in Bentley, and then you want to transfer it over to Esri or have it live reference in. This is the standard that does that. Anyway, this is being developed right now, and it's in draft format, but it looks, all your major application developers comply with OGC. When you collect the data in accordance to ASCE 38 and ASCE 75, you're set for going forward. And again, we want to enable all these great technologies that are out there and really enhance the damage prevention and use augmented reality. And the incremental cost is not a big deal. We've already shown that, especially with the technologies out there today, and the achieved benefits really dwarf the costs. There was a study done. I mean, we know that subsurface utility engineering brings value to projects, and there's all kinds of studies that demonstrate that. This NCHRP paper that was done just 2 years ago, we basically were able to lean on what the value from Sioux and project that there's going to be tremendous values from just document it when it goes in the ground in the first place. And thank you very much.
Thank you so much, Phil. That was great. Very, very detailed. That's certainly the most I've ever learned about that standard.
That's a drinking from a fire hydrant. But sorry.
Oh, that's what we're here for, though. This is what this event's all about. So thanks for presenting that. It was very important.
My pleasure.
So we've got a question in from the audience. Are the ASCE 38 and 75 new standards going to be released soon?
Yes, they should be. I would expect they're in the pubs right now. If Jim Ansbach was on here, he could probably tell you more accurately, but my understanding is we're looking at about 6 to 8 weeks.
Is there anything you wanted to leave the conference with?
No, I think this is a tremendous conference, and I'm really excited. I mean, this is exactly why we wanted to develop these standards, and we started out 9 years ago. We knew these technologies were coming out for both collecting the data and then leveraging the information. So I hope to be able to participate in your upcoming conferences and help share these standards and make sure they're adopted going forward.
Thank you so much. Yeah, these standards are so important. They allow us all to work together. So thanks again, Phil.
My pleasure. Thank you.